Well, hello everyone. It's a pleasure to be here. Hello everyone watching online. Hello everyone watching on YouTube later. So, my talk is a magical journey through advanced mathematics. I'm Ricardo Teixeira, and inspiration for this talk was the book that was released during the pandemic. So it's called A Magical Journey Through Advanced Mathematics. And then a little bit about myself. I'm a mathematician, but I love magic tricks, and also I'm a big fan of Martin Gardner. I'm associate professor of mathematics at the University of Houston, Victoria. And then these are some topics. One of the questions that I have is, can we give magic trick examples in every advanced math course? And also, can we introduce math areas using magic tricks? So these are the topics that I normally cover in my courses. Proofs, probability, abstract algebra. So there are a lot of topics that I teach or I'm at least interested in. So there are 12 topics here. That's the 12 chapters on the book. So for example, for proofs, we use a Penn and Teller's trick that they do in their shows and also in some TV shows. In this trick, they use 4 cards. So we developed using finite induction, a version with n cards, and then we proved that the trick would work for any number of cards, including 14 cards. That's my attempt to put 14 at least once. So for abstract algebra, we have this. If you know a little bit about magic, this is size tables, and then we related this to group theory. So there's a way of kind of prearrange the deck of cards. So there's a lot of nice tricks that can be done with size tables. There's an article that I published in the European Gather for Gardening, organized by my friend George Nuno Silva. So you can take a look at this. For linear algebra, we have magic squares. The sum of every row, every diagonal, and every column is 15. We try to use this whenever we talk about linear algebra. For example, if you take the magic square and put this in terms of a matrix, so if you multiply this by a vector having only ones, you're going to see that the result is actually the sum of every row, so it's 15. So you realize that 15, 15, 15 is a multiple of 1, 1, 1. So this is just saying that this 1, 1, 1 is always a eigenvector, and that sum of the magic square is what's called the eigenvalue. There's a lot of more linear algebra that can be done with magic squares. For coding theories, in the last gathering for Gardner, I posted a lie detector magic trick. For this year, I've created a new version of this trick. Last time was a binary trick, now it's a ternary trick. So it's in the exchange book. Topology. We can talk about topology, and my friend Tiago is the expert of magic with ropes. But we do a lot of topology tricks. So for example, we analyze one Chris Angel's trick, but we talk about the winding number. So in the trick that Chris Angel does, he magically puts a chain through his neck. But then if you analyze, and the explanation for the book is that the winding number of the chain with respect to Chris' neck was actually 0. So that's the trick that has been done. For geometry, okay, we talk about concepts of Euclidean, non-Euclidean geometry. We can talk about magics with mirrors. But one of the tricks that we have to explain is, for example, some cards will have what's called a rotational symmetry. Some cards would not have this rotational symmetry. So the result after 180 degrees is different. So we can do magic tricks using that. For real analysis, that's one of my favorite chapters. We can start with any 3-digit number. For example, 425. And then we create a sequence of numbers. How so? The next number will be the difference between the biggest number that can be formed with the previous number minus the smallest number that can be formed with the previous number. So for example, in this case, I rearrange 425 as 5, 42 minus 245. And the result is 295. And then x3 would be exactly the same thing with x2. We arrange them in decreasing order, subtract from increasing order. So if we do this, well, we see that this is a sequence of numbers. So we can do this infinitely many times. So we know that it's a bounded sequence. It's not necessarily, at least at first, it doesn't have to converge, but it will have a subsequence that converges. And because it's a discrete, every sequence that converges will be constant after a while. So for example, for this example here, once we reach 495, then all of the next numbers will be 495. So it didn't have to converge, but it does. So, but the interesting thing is, it doesn't matter which is your initial number, it's always going to converge, and it's always going to converge to 495. This is called Kappa-Kar's constant. Okay? For history of mathematics, we have a Fibonacci trick. It's pretty much create like a Fibonacci-like sequence, which we created any two numbers, and then you just created 10 numbers, and then you ask someone to add these numbers, but the addition would be just the seventh number of this list times 11. So there are amazing possibilities that can be done, and students seem to enjoy a lot. So thank you very much. If you want to contact me, that's my Instagram. So, thank you.